Welcome back to my channel. Today I'll be showing you proofs of the factor and remainder theorems. So first we'll be looking at a proof of the remainder theorem, then we'll be deriving the factor theorem from it. So here I've written the remainder theorem for you. The remainder when a polynomial p of x is divided by x minus a, where a is any real number, it's a constant, is p of a. So to prove this, we will need to use something called Euclid's division lemma, and I will show to you what that means right now. So let's say we are doing a simple division operation between natural numbers, such as 5 divided by 3. We are working in the natural number, so we don't have the real number solution, which is 1.666 dot dot dot. So if you give this problem to any student, he will say that the quotient is 1 and the remainder is 2. So what Euclid's division lemma does, it provides us a relation between these four numbers, and here's what it says. When a is divided by b, we get a quotient q and a remainder r such that a is equal to bq plus r. And you can verify this. In fact, we have 5 here. 5 is equal to 3 into 1 plus 2, 5 equals to 5. So this lemma is true for the natural numbers, but a similar lemma also exists for polynomials. So this basically states, when you divide p of x by g of x, you get a quotient q of x and a remainder r of x such that p of x equals to q of x into g of x plus r of x. So we'll be borrowing that relation over here for our proof. So p of x, the polynomial which is we have, equals to q of x, and here the polynomial we are dividing by is just simply x minus a. So we can write this as x minus a plus r of x. And now another thing you need to know is that the g of x which we are dividing with, it's a linear polynomial. So the remainder, it will always be a constant term. So rather than writing r of x, we can simply write it as r. So this is a relation which we have, and it will be true for all values of x. So it's basically an identity. So what we want to do, we want to isolate this r. So we want to make this 0, so we can get r in terms of p of x. So if you want to make this 0, we can simply make x minus a 0. So if x minus a equals to 0, then obviously if we add a to both sides, we will take x equal to a. So as soon as we do that, p of x will become p of a, since x is equal to a. This term will become 0. So q of x into 0 will simply be 0, and what will be left is the r, which is the remainder. So the remainder when the p of x is divided by x minus a is p of a, and this is our proof complete. So now we'll be proving the factor theorem, and we can easily derive this from the remainder theorem only. So this states that if p of a is equal to 0, then x minus a is a factor of p of x. And the way we'll be proving this, first we'll assume that p of a equals to 0. Assume that p of a equals to 0. Then the factor theorem says the remainder when p of x is divided by x minus a is p of a. So therefore the remainder when p of x is divided by x minus a will also be 0. So we can write that down. Then the remainder is also equal to 0. And when we say that something is divisible by another thing, for example, if we say 6 is divisible by 3, the reason for that is because it leaves a remainder of 0 when you divide 6 by 3. It doesn't have any fractions. So this is basically what we are saying. P of a equals to 0, then the remainder will be equal to 0. So when p of x is divided by x minus a, the remainder will be 0, and that is the definition of a factor. So from this we can say that x minus a is a factor of p of x, and this concludes our proof. We have shown that if p of a is 0, then x minus a must be a factor, which was the condition of the theorem.